Hi, this is Mrs. Henry. Today we're going to talk about Hardy-Weinberg equilibrium and how we use that in population genetics to determine if evolution is happening. Our learning target is to be able to evaluate data-based evidence that describes evolutionary changes in the genetic makeup of a population over time. We use the Hardy-Weinberg principle to determine if evolution is happening, and we do that by calculating allele frequencies and then looking for changes over a long period of time. The Hardy-Weinberg principle states allele frequencies in a population will remain constant in the absence of evolutionary changes. When we use Hardy-Weinberg, we make some basic assumptions. First of all, we assume that no mutations are occurring, that random mating is occurring, that we have a very large population size, no selection is happening, and there's no immigration or emigration. So we're going to work with this population of bears to start out with. We have a homozygous dominant brown bear. We have a heterozygous dominant brown bear. And we have a homozygous recessive gray bear. So here's our population of bears. 75% are brown, 25% are gray, but that doesn't tell us the frequency of the alleles. That just tells us the frequency of the phenotypes, and we're really after the genotypes and how many alleles we see. So we're going to start with the first equation that says P plus Q equals 1, where P is the percent of dominant alleles and Q is the percent of recessive alleles. We can't get that just by knowing the percent of the phenotypes, so we have to add a second equation. Since we can't know the number of alleles or the frequency of the alleles by using the P plus Q equation and by looking at this picture, we have to use the expanded equation. And the expanded equation shows us percent in the population of each of these phenotypes. So P squared is the percent of homozygous dominant that we see, 2PQ is the percent of heterozygous dominant, and Q squared is the homozygous recessive. We can't see inside these brown bears and tell what their genotype is, but we do know that these little gray bears are homozygous recessive. So let's use that. So 25% of these bears, or 1 out of 4, are gray. So that makes our homozygous recessive number 25%, but we don't want to state it as 25%. We want to change it into a decimal, so that's 0.25. That means Q squared equals 0.25. How do we find Q? Pretty easy. The square root of Q squared would be Q. So the square root of 0.25 is equal to 0.5, and that equals Q. So now we know what Q is. If we go back to our equation that says P plus Q equals 1, and we know what Q is, because it's 0.5, then we know that P has to also equal 0.5. Now we know what Q is, and we know what P is. And so all we have to do is substitute those into this equation. So now let's put that into our formula. So P squared is going to be 0.5 squared plus 2 times P times Q plus Q squared, which is this. So if we do all the math, this is 0.25, this is 0.50, this is 0.25. So that means we have 25% that are the homozygous dominant, 50% are heterozygous dominant, 25% are homozygous recessive. So what do we do with that? We look at these numbers over a period of time, look at the allele frequencies, look at the phenotypic frequencies, and if there's no change, then we can assume evolution is not happening. And if there is a change, and we can eliminate all of those things that were under the Hardy-Weinberg assumptions, then we know that evolution probably is happening. Let's look at another example. So we have two penguins here. Our guy up here without wings is the dominant form, so we know that that's going to be both homozygous and heterozygous dominant. And this one with the wings is our, we're going to use little p's here, this is our homozygous recessive. We always know that because the only way you can see the recessive trait is if both alleles are recessive. And we're going to say that we have 36% of our population in the homozygous recessive form. That's our Q squared, so we want to solve for Q. So Q is just the square root of 36, which is 0.6. And now we can solve for P. So P is going to be equal to 1, because remember P plus Q equals 1. So 1 minus 0.6 equals 0.4. So Q is equal to 0.6. P is equal to 0.4. Do they add up to 1? Yes, they do. So now we can go ahead and plug those into our expanded equation. So let's drop those numbers into our expanded equation. So for P squared, we had 0.4 squared. And then 2PQ would be 2 times 0.4 times 0.6, because that's our Q. And then for Q squared, we had 0.6 squared. So if we do the math, we have 16% that are homozygous dominant, 48% that are heterozygous dominant, and there's our 36% that are homozygous recessive. So let's do one more, and you might want to pause and try this before you see my answers, just to make sure that you have it. So we're going to start with these bunnies. We have pink as the dominant and tan as the recessive, and let's say we have 16% of these homozygous recessive tan bunnies. So that's an easy one, because we know that this is Q squared. Therefore, Q is going to be the square root of 0.16, which happens to be 0.40. So we can plug that into our equation. P plus Q equals 1. What plus 0.4 is going to give us 0? P is going to be 0.6. So you can just do that part in your head. And then we want to plug it into our expanded formula. Okay, so here we go. P squared is going to be 0.6 squared. 2PQ is going to be 2 times 0.6 times 0.4, and then Q squared, we already know what Q squared is, right? It's 0.16, but we'll just do this just to make sure that we're following our equation. And then the answers, this is going to be 0.36. We already know this is 0.16. And this is going to be 0.48. Do they all add up to 1? Yes, they do. So that's Hardy-Weinberg. If you want more practice before lab, you will find some practice problems on Moodle. Otherwise, I will see you in the lab.